Welcome back to our video series on transport transforms and other Lagrangian representations for signal image data. In this video, we're going to talk about the connections between the cumulative distribution transform, or CDT, and one-dimensional optimal transport. So if you remember, in the past videos we defined what we call the cumulative distribution transform, or CDT. And just like the Fourier transform or wavelet transform, we can think of the CDT as a transform or representation tool that takes us from signal space to a transform space, which we call the S hat here, the hat referring to the notation of the transform of S. And in the case of the CDT, or the cumulative distribution transform, this S hat is simply the function f that maps the cumulative integrals of our original signal S and the cumulative integrals of the integral of a particular reference, a chosen fixed reference, S naught. And if you remember, for example, we can choose a variety of functions to be our reference function, S naught. The simplest choice is the uniform distribution, right? The chi function between 0 and 1, let's say. Then, via the formula we explained before, the cumulative distribution of the uniform distribution is simply x, and our transform is simply given as the inverse function of the cumulative distribution of our signal little s. And if you use this as particular S naught as a representation, as a reference function with which to build a representation for our signal, then we can define a Fourier transform as simply the inverse function of a cumulative distribution of S. And that's our Fourier transform, and we can also take this Fourier transform and go back to our original function space, and we do the reverse operations that are necessary to get us back, which namely mean first taking the inverse of S hat and then differentiating, right? And we saw in this case, this means just the following two very simple operations. You take your original signal, compute the CDF, and then you flip the axis of the CDF. So in summary, we can think of the CDT as an invertible nonlinear signal transform. In other words, we can think of a signal S of x, or we can represent the signal as this function f of y, which is what we called the transform of S, and we denote the transform as S hat. Okay. So this S hat, or this transform f, is a mapping from the domain of a reference function S naught to the domain of our original signal S of x. The way this mapping function is computed is by first integrating both of the signals. So capital S here is the integral of S, and a capital S naught here is the integral of S naught. And then finding f of y such that these cumulative integrals are matched, right? And as we explained before, because these functions S, capital S, and S naught are increasing functions one-to-one, taking advantage, we define these signals here to be positive, then this f exists and is well defined. Of course, we can write this equation in integral form as here, or we can differentiate both sides with respect to y, and we get this alternative form here. And again, y belongs to the domain of our reference function, right? So in summary, we can think of the CDT as an invertible nonlinear transform for signals which are smooth probability density functions. So each point in this yellow space here corresponds to a probability density function, and we can take any point here and find out what is the corresponding point in transform space, which happens to be the set of all one-to-one diffeomorphisms between the domain of the reference and the signals, and that's why we can think of the signal in the space or in transform space, and they're more or less equivalent in that the entire information about the signal is represented in both spaces. Just like the Fourier transform, for example, will have certain mathematical properties, as we explained before. So does the CDT. The first, or the simplest one to understand, is the so-called translation property of the CDT. So let's imagine we have a signal S of x here, and let's imagine we have a translated version of the signal S mu of x here, which is simply the original signal translated by mu. We have derived that the transform of this translated signal is related to the transform of our original signal, and the only difference is we add this mu, this translation mu here, to the transform, and that's the result. Similarly, we can derive the scaling property, and more generally, these are examples of what we call the composition property. Let's say we have a signal S of x, but instead of observing the signal, we observe some Sg of x, which is some kind of transportation via this one-dimensional increasing mapping function g. Then if we compute the transform of this Sg here, we'll have that this is simply the inverse function of g applied to our original transform. And the main idea here is that this transform helps convert what we call Lagrangian deformations, borrowing from the PDE nomenclature, right? So we have our original signal here, and we can obtain a version of the signal Sg by simply pushing the intensity of the signals around by certain necessary amounts. And in transform domain, what will happen, instead of pushing in the independent variable domain, this pushing will be reflected in the dependent variable domain. As we explained in our previous video, one good reason to represent your signals in transport transform domain rather than original signal space domain is so as to render signal classification problems easier to solve. For example, let's say we have a problem that consists of signal classification of 3 classes. The blue class is signals with 1 bump, the orange class signals with 2 bumps, the green class signals with 3 bumps. And let's imagine that these can be observed under any random translation along this independent variable domain. If we try to fit a linear classifier on some training data and measure the performance of this linear classifier in test data, as you can see by the plot on the right, we're going to make a significant amount of errors. However, if we take this training data and represent it in transport transform domain, and repeat this exercise of using training data to fit a linear classifier and then project test data onto this linear classifier, we'll see that we're going to be much more successful. So how is the CDT related to one-dimensional optimal transport? So let's start once again with our signal that we would like to transform and our chosen reference, which in this case we chose to be the uniform distribution once again. And as we just discussed, if we integrate both of these signals and then ask to find the mapping F that matches these integrals, we can express this equation in integral domain or differentiate both sides of this equation to represent this matching in signal domain. And the function f that solves this problem is what we call the transform of the signal S0. And we also had a video about how to compute an approximation to this function f of x. One interesting thing about this function f of x is that for signals which are non-decreasing, right, which means these signals are either 0 or positive, this mapping function can be defined uniquely, right? This mapping function that once again maps the domain of a reference signal to the domain of our signal. And this leads us to optimal transport. And the starting concept about optimal transport can be stated in 1D very simply, and that is in the form of a function that measures the effort that it takes to rearrange the signal S0 onto the signal S, or vice versa, right? So if we imagine measuring the cost to transport a particular parcel of the signal S0 here, so that we'll have to perhaps move some signal from here onto some portion here, and we measure what the distance we had to move that particular signal times the amount of mass that we had to carry to match these two signals. This is the so-called Munch functional. And optimal transport is defined as the minimizer, the function f that minimizes this Munch functional. Now, in the one-dimensional case, as we just stated, this mapping function is unique. In other words, there is only one f of x. That makes no sense to even talk about minimizing it, although it's not technically wrong, because there is only one. Naturally, the one that we found is the minimizer of this function, and in which case, it's the minimum cost to rearrange the signal s naught onto the signal s of x, right? And once again, this f mapping function that rearranges these two signals is what we called the CDT of our signal. So this is how these two concepts are related. And the minimizer of this function, this functional, called the Munch functional, is what's called also the Wasserstein distance. Now there are many kinds of them, and in this case we're using the squared Wasserstein distance, where here we have a square measuring square of the displacement field as the cost of rearranging them. We could have chosen to have another number here, 3, 4, 1, etc., and these are related to different so-called Wasserstein distances. But this is the most common one, and this is called the squared Wasserstein distance. So this concept of optimal transport or optimal rearrangement of signals or signal masses is due to Gaspar Munch, who was originally looking at, let's say, civil engineering or construction problems, where he wanted to consider very carefully the amount of effort that it would take to rearrange a pile of sand, perhaps in the ground, onto a particular form, let's say a castle, right? And so let's say our signals S1 and S2 here are the densities corresponding to these measures, right? This problem of optimal transport is typically expressed in measure theory. So for now here, we're just giving a historical overview. We may go into measure theory in a few videos down the line, but the idea is to find this mapping function f of x that maps the domain of one of these piles of sand onto the other one, such that the amount of effort as quantified by the total displacement f of x minus x times the amount of mass that has to be displaced for that particular point is minimized. That's so-called the minimum effort, right? And this is a rich theory which began centuries ago and has particularly interesting developments in the past couple of decades. The point on this particular video is not to go into detail here right now. We may go into later on in subsequent videos. So from the application point of view, from the data science point of view, why should we be interested? Why is it interesting to consider optimal transport or Wasserstein type distances as we just discussed? And briefly, the answer has to do with allowing us to be more successful in solving certain kinds of optimization problems. So let's say we have two signals here, P of t, here now our independent variable is t for time, and we have our signal P of t, which is this blue curve here. And let's say we have another signal which we call Q of t, which is also parameterized by this tau here, which is once again our signal P of t translated by tau. And so let's now measure a function. Let's now quantify the distance between these two functions and quantify this distance as a function of this displacement tau here, right? And let's quantify this distance using the standard Euclidean distance between them, the L1 distance, or the integral absolute values between them. Let's also compare different kinds of divergences used in machine learning and data science. And let's compare to this so-called this squared or two Wasserstein distance, right? So as we take this dotted red curve here and translate with respect to the blue curve and measure the alignment between them using these different distances, you can see that most of these other distances are actually mostly local, meaning when this red curve starts overlapping the blue curve, that's when these distances start being able to tell a difference, right? Over here, when these curves are not overlapping, uh, you know, there is no difference as far as this distance can see on the parameter tau. We change the parameter tau a little bit, these distances cannot tell the difference, right? Now, when we're close to the optimal alignment, then yes, then any of these distances will be good enough as far as measuring their misalignments, but not when you're far away. Now, this is not true for the Wasserstein distance that we just discussed, right? As you can see, no matter what the alignment is, the distance here is basically the parameter tau, right? And in this sense, the Wasserstein distance can see far, right? Meaning no matter what tau it is, even if tau is very far away, the distance will be able to point you in the right direction as far as solving this minimization problem of aligning P and Q here. So now we arrive at the main claim in this presentation, in that the Wasserstein distance between two of our signals S1 and S2 can actually be expressed as the Euclidean distance, or some weighted form of the Euclidean distance between their respective CDTs, or the transforms of S1 and S2, right? And this is known as the Wasserstein embedding theorem, which is a very well known. So let's get a gist for why this is true. So let's define S hat as S1 hat as a transform of signal S1, S2 hat as a transform of signal S2. That is, this S1 hat and S2 hat functions are functions such that if we compose and transport our signal S1, we get our original signal, reference signal S0. And once again, this Y variable is in the domain of our reference signal. So in this case, for example, S1 hat is a mapping from the domain of our reference signal to the domain of our S1 function. S2 hat is a mapping from the domain of the reference signals to the domain of the S2 function. Let's further define what we call this h of x function, which is the mapping function that relates S1 to S2 via this equation here, right? That is, using the composition property of the CDT, we can also claim that as taking the CDT of these both sides here, that S1 hat is H inverse composed with S2 hat, right? Or in other words, we can apply H to both sides of this equation, right? Because H here is, we're assuming to be a one-to-one increasing function. So S2 hat can also be represented as H composed an S1 hat. So now let's plug this into our Wasserstein cost, right? So the Wasserstein distance between signal S1 and S2 is given here. This is from our previous slide. This is just the displacement between that rearranges S1 to S2 in the form of this equation here, right? So this is the Wasserstein cost, which we just copied from the previous slide. Now let's apply this change of variables. Now, instead of expressing this integration with respect to the variable x, let's apply change of variables, and let's express this as an integration with respect to y, which will be a function S1 hat of x, right? Which we already defined as a transform of S1. If we plug this into here, right, so every time we see x, we plug in S1 hat of x, right? And so here it goes, x goes there, S1 hat goes there, S1 hat goes there, right? And S1 hat goes there, and we also have the change of variables theorem. We also have to have the first derivative of this mapping function S1 hat, right? And that's now, and we also apply, of course, the domain of this integration has to be changed, and here's the equation, right? And using these assumptions, that the statements that we made up above, right, where S1 hat is a mapping from the domain of the reference to the domain of signal 1, right? And just as we expressed over here, and that S2 hat is related to S1 hat via this H mapping function. So every time we see, right, so this here, we're going to simplify that. And here we see that this guy here is simply S not hat, right? And once again, H of S1 is simply S2. So we plug all that in and we can see now that the Wasserstein cost can be written as a function, as an integration, as a difference between the integration of S1 hat and S2 hat. But this different, this, if this wasn't here, this would be straightforward Euclidean difference, distance defined on this omega naught interval here, right? So we can write this as sort of some kind of weighted Euclidean distance, with the point being, once again, that if we would like to compute the Wasserstein distance between these two one-dimensional probability density functions, S1 and S2, we can do this if we want by simply computing their transforms and subtracting them and taking the weighted Euclidean distance with the weights being the reference function as S naught. Once again, if we choose the S naught function here to be our uniform distance, this is simply 1, and this becomes our standard Euclidean distance. So in summary, we tried to relate the cumulative distribution transform here to one-dimensional optimal transport. And the main statement is that the CDT is related to optimal transport. That is, the Wasserstein distance between two signals can be computed as the Euclidean distance between the respective cumulative distribution transforms. Right? And the other point that we try to make is that the Wasserstein distances can see further and can be useful in engineering applications involving optimization. The example we gave is the alignment of these two functions here, right? All of the other distances that are typically used in engineering and data science, they start becoming meaningful when these signals overlap each other, they align, so then they can tell the difference between one tau versus another tau. But once they're far away from each other, none of these distances can tell one tau from another, and hence if you're using some kind of gradient descent type optimization or some other minimization method to find this alignment, which it's very common in many engineering applications, as we'll see. These typically used distances are not very informative, they're sort of blind. The transport distances, like the Wasserstein distance, for example, they can see farther, and you would be able to find this alignment using a gradient descent technique, even if you started relatively far off from the optimal alignment.